next presentation will be Konstantin Shishmarev from Harbin Engineering University. This is a joint work with Aglezhneva and Habapasheva. Please, Konstantin, you can start, please.
Okay, thank you, Yuri. Dear colleagues, good day. I would like to thank the organizers of this workshop for the opportunity to present results of my colleagues and my own work. Today, I will speak about periodic hydroelastic waves propagated in a frozen channel with non-uniform thickness of ice. In this presentation, I will introduce a method of the solution for such a problem and show its implementation on one simple example of non-uniform thickness of ice. Motivation to study problems in channels comes from, in general, 2 points. First point is that distributions of ice deflections and strains in the ice cover can be very different for ice cover in a channel and unbounded ice cover. As illustrated here, for the problem of motion of a load, in some cases, maximum strains can be near the channel walls, but not under the load as it was expected by the model with unbounded ice cover. The second point is that in the channel, there exists infinite number of periodic waves with different wave profiles and different wave characteristics propagating along the channel. However, only few of these waves contribute to the ice response for any external load. We can see the channel with a rectangular cross section. In the x direction, the channel is unbounded. Fluid in the channel is incompressible and covered with a thin ice cover. The thickness of the ice cover in the y direction across the channel can be arbitrary. It can be of any shape. These examples of this shape are presented on this slide. In the x direction, the ice thickness does not change and remains constant. This problem is solved in the linear theory of hydroelasticity. Formulation of the problem in this theory is a classical. We have an elastic part describing dynamics of the ice cover as an thin elastic plate, and we have hydrodynamic part of the problem describing the fluid flow in the channel. Here in this problem, fluid flow is caused by vibrations of the ice plate. We can see the ice frozen to the channel walls, which modeled by Eckland conditions. Main difficulty here is in the plate equation. There is this differential operator, which has this complex form. It's because the ice thickness is a function of y. If ice thickness is constant, then only usual term with fourth derivative shown in the blue box remains in this differential operator. This problem is coupled and the elastic and the hydrodynamic parts connected through kinematic and dynamic boundary conditions. We look for a solution in the form of waves propagating along the channel with constant speed and constant amplitudes. Then for the wave profile, function f and the potential profile in the cross section of the channel function phi, we arrive at this boundary problem. This boundary problem is written in dimensionless variables. Frequencies and wave numbers are included in some coefficients of these equations. And in this formulation, we don't need for initial conditions, conditions at infinity, and any external loads. Third case that we have studied is fully linear or symmetric linear ice thickness across the channel. The main idea here was that wave profile across the channel can be solved as an infinite series of Bessel functions. Parameters and coefficients of these Bessel functions can be calculated, and then we can obtain dispersion relations and other wave characteristics using the method which I will show further. In this presentation, I will focus on a solution for arbitrary thickness using this Weis linear approximation. We start to solve this problem by searching the wave profile across the channel function f. We divide width of the channel by small segments and approximate shape of ice thickness by linear functions on each segment. How this can be done is shown on the top of this slide. For this simple example, only 3 segments enough, but in a general case, the number of segments can be much larger. We seek wave profile across the channel in the form of infinite series of modes psi n. These modes will be also piecewise, and we seek its own solution on each segment. For any different shape of ice thickness, these functions should be calculated again. For piecewise linear approximation of ice thickness, there could be 2 cases. First case, when ice thickness is constant, then the plate equation reduces to this simple form, and we can seek a solution in the form of standard normal vibration modes of an elastic beam with constant thickness. In other cases, ice thickness will be a linear function. In this case, plate equation remains complex, and we can seek a solution in the form of normal vibration modes of an elastic beam with linear thickness. For both, it's easy to show that if ice thickness is constant, then its derivative is equal to 0. Then these 2 terms disappear, and plate equations will be the same. For both spectral problems, solutions will be these functions. For plate with constant thickness, it will be a combination of cosines and sines, including hyperbolic ones. For plate with linear thickness, it could be a combination of 4 Bessel functions. Now, taking into account each solution on each segment, these functions describe the normal modes psi m of beam oscillations for this given shape of ice thickness. Now let's see what conditions and how many conditions we will need to obtain to calculate coefficients A, B, C, D on each segment. In total, we need 4 times number of segments plus 1 condition. First, 4 conditions can be obtained from the boundary Coulomb conditions and the channel walls. Next conditions we can get at the boundaries between segments. Here at these places, ice deflection, slopes, bending moments, and shear forces should be continuous, and taking into account the same rigidity of ice on each segment, these conditions will have form as it's shown in the big red box. The last needed condition is the orthogonality condition of modes psi n with a weight, whereas weighted function is a piecewise linear approximation of shape of ice thickness. From here, we can calculate modes psi n. Now let's see how we solve problem of hydrodynamic part. The potential profile in the channel section is also solved in the form of an infinite series of functions Pn multiplied by the same principal coordinates an. Then solution for each function Pn can be obtained from this boundary problem and can be expressed in the terms of functions n calculated earlier. Since we consider non-uniform shape of ice thickness, both even and odd parts of the solution for the potential profile should be taken into account. Then we substitute both series for wave profile and for the potential profile into the plate equation. Then we multiply by any one mode psi n and integrate the result across the channel. Next, we take a finite number of modes psi n and obtain this matrix problem. The advantage of constructed modes psi n is that they are orthogonal, so we can be sure that all matrices in this matrix problem will be symmetric. The dispersion relations are solved as eigenvalues of this matrix, and corresponding principal coordinates an are solved as eigenvectors of this matrix problem. Then, once we found dispersion relations, we can calculate phase and group speeds and then find wave profiles across the channel and maximum strains in the ice cover. Now I will show implementation of this method on one simple example. This shape of ice thickness is considered with such a linear piecewise approximation of this shape. All parameters used in our calculations were equal to the parameters of the experimental ice tank shown on this slide. Even for this simple piecewise linear approximation, there will be many input parameters. The main parameters are average thickness of ice on each segment and angle of inclinations on linear segments. In this case, there will be 3 average thicknesses and 2 angles of inclinations. We keep total average thickness of the ice in the channel equal to declared thickness in the ice tank. And we considered 3 different cases of calculations marked by different colors. These cases are when average thickness on the left segment is equal to or 1.5 or 2 times larger than average thickness on the right segment. And for each colored case, we considered 3 subcases with small, medium, and large linear changes in thickness on linear segments. Here you can see parameters of the calculations of that case. First, let's discuss convergence of the results. Here you can see dispersion relations, phase and group speeds of the first waveform for the lowest frequency. Black line show results for the plate with constant thickness, and blue line with blue markers show results of the corresponding blue case. Here, linear change of ice thickness on the left and right segments are very small. And for this case, all these wave characteristics visually are almost the same. Same conditions holds for the waveforms with larger numbers, with larger frequencies. For example, for the staggered waveform with the next to the lowest frequency. Now let's see what happens with these wave characteristics if we consider ice thickness with a large variation. Here you also can see distribution relation space and group speeds. Black line shows the results for the plate of constant thickness, and the colored lines show the results for the corresponding blue, red, and violet cases. In all of these calculations, average thickness on the right segment of shape of ice thickness is equal to 5 millimeters, when total average thickness in the channel is equal to 3.5 millimeters. And yes, we can clearly see a large difference in all of wave characteristics, especially for large wave numbers. And we can say that considering ice with variable ice thickness leads for this shape leads to reducing of values of all these wave characteristics. One important thing that values of critical speeds, which are very important for operations on ice and which are equal to the minimum of phase speed, can be very different for plate with constant thickness and plate with variable thickness. This difference is shown on the plot for the phase speed. The maximum difference for this case is will be for the violet case, and the value of critical speed for plate with constant thickness is about 2 times larger than value of critical speed for the violet case. Same conclusions holds for the wave numbers, for the waveforms with larger numbers and larger frequencies. For example, here you can see results for the second waveform with the next to the lowest frequency shown by no sound.
Can you please ask? Is that now?
No, it's okay.
Now it's okay?
It is, yeah, now, yes.
Okay, maybe we have some connection problems. Okay, so the same conclusions holds for the waveforms with the largest numbers and the largest frequencies. For example, for the waveform with the for the second waveform with the next to the loud frequency. Results for the wave profiles and the maximum strains along the phase will be shown for both short and long waves. Here you can see wave profiles across the channel for the first waveform with the lowest frequency. Here short waves means that its wavelength is 5 times smaller than channel width. Calculations were performed for all 3 cases and for 2 subcases with a large change in ice thickness. These results are shown by thin line, and a small change in ice thickness. These results are shown by thick line. And we can see for short waves that for all cases there is a shift of maximum amplitudes towards center of a middle segment where ice become thinner, and on the left and right segments where ice become thicker, we can see that there is a large decrease in amplitudes of waves. Here you can see maximum strains along the phase plotted as functions of I. Parameters of calculations are the same as for the previous slide. Black lines show results for the small change in ice thickness, and orange lines show results for the big change in ice thickness. And what we can see here for short waves, maximum strength will be again shifted toward the center of the thinnest part of the ice cover, and direction of the strain will be along the channel. Strains at near the walls will be very small compared to the strains in the middle of the channel. And we can say that considering ice thickness with variable thickness, it leads to reducing of values of maximum strains. For long waves, results are more complicated. Here you can see profiles of these waves. We can see that for big linear change of ice thickness, there will be small rare oscillations of wave profiles along the profile. And here you can see maximum strains along the phase. For long waves, principal difference is that here amplitudes of maximum strains themselves will be much lower compared to the maximum strains for short waves, and for ice with more or less constant ice, constant thickness, maximum strains will be at the channel walls. And considering ice with variable thickness, we can see that maximum strains will decrease at the channel walls, and also we can see large values of maximum strains at the point between left and middle segments. So here the conclusion of this presentation, and the main conclusion is that even a very small angles of inclination of ice thickness can lead to a big change of wave characteristics, wave profiles, and critical speeds.
Thank you for your presentation, very clear. And now questions, please, from audience. Any question, please? Okay, one question from you. Consider it lowest harmonics or some higher harmonics also?
You mean what? You mean values of frequencies?
Yeah.
I can show you this plot. It's didn't show it yet, but you can see. Yeah. So this left up picture. This is values of frequencies which we consider. So it's about to 20, from 0 to 20.
But they are discrete. Now I can see continuous. But frequencies are discrete.
It's here in this problem, frequency is a function of wave number.
Yeah.
So and this is how it looks. It's calculated. It's calculated frequencies as functions of wave numbers, and yes, it can be calculated for any positive wave number.
Okay, understand. And another question: you consider it linear change of the thickness? Did you consider it piecewise constant change of this thickness?
No.
Is it easier or more complicated?
I don't know. The main idea was that let me show you these conditions between segments. It's in the big red box. Ice deflection, slopes, bending moments and shear forces should be continuous through full
Through length.
through width of the channel. So
So it's maybe, yeah, I understand, it's physically not correct to use pi-square constant. Therefore, because condition at the boundary cannot be provided physically. Thank you.
I have a question. How do you consider short waves and long waves?
It's it's a good question. It's what we mean about short and long waves. I said that we mean short waves. It's maybe 5, maybe 10 times less than width of the channel. In this sense.
Okay.
And long waves for these calculations, wavelength is about 1.4 width of the channel. So more or
means
less
it's
than,
not like that KH.
No.
It's depending on the depth of the channel.
No. It's
Okay. Thank you.
In your solution, you used Bessel functions.
Yeah.
Can you explain what is necessary to use this type of function?
It's because in this solution, when we use piecewise linear approximation, we want to find the solution on each segment. And if we consider segments with linear change of ice thickness, then plate equation will be as it's shown in the bottom left box. And this equation can be solved by introducing these spectral functions psi and t. And this spectral solution of this spectral equation will be Bessel functions. So it's like it's not we wanted to use Bessel functions, but they arise.
They have to be.
They have to be here
Solution
because of this type of situation.
Thank you. Any other question, please?
No question.
How long time takes calculation? For example, you used 20 harmonics, yes?
Yeah, yes, to get sufficient results, maybe 20 is enough, maybe more than enough. It's like we should calculate because it's a semi-analytical approach. We should calculate eigenvalues of this matrix, and actually these coefficients in this matrix were quite good, and calculation did not take a long time. Right? It's very fast calculations.
Thank you. Any other question, please?
Maybe.
Okay, then we thank you, Konstantin,